Now let's summarize our approach. We have this polynomial a of x of degree at most n minus 1, and we want to evaluate this polynomial at two endpoints, x1 through x2n. And we get to choose these two endpoints however we want. And we're looking at how we choose these points. One very minor point that I want to identify now is why we consider this polynomial at two endpoints instead of endpoints. And in fact, later we'll go back and we'll look at it at endpoints instead of two endpoints. But for now, we want this polynomial a of x at two endpoints. Why? Because of our application to polynomial multiplication. Recall, our first step in our construction is to define this pair of polynomials a even and a odd. We do this by taking the even terms of a of x to define a even and the odd terms to define a odd. Whereas the original polynomial a of x was of degree at most n minus 1, each of these polynomials is of degree at most n over 2 minus 1. So the degree went down by half. Next, we recursively run the FFT algorithm on this pair of polynomials, and we'll evaluate these pair of polynomials at endpoints. What are the endpoints? The endpoints that we evaluate this pair of polynomials at are these points y1 through yn, which are the squares of these two endpoints. Since the original two endpoints satisfy the plus-minus property, then x1 is the opposite of xn plus 1, so the squares are the same. That's our first point, y1. x2 is the opposite of xn plus 2, so their squares are the same, and that's y2. And so on up to yn, which is xn squared and x2n squared. Why do we want this pair of polynomials at the square of these two endpoints? Well, recall, to evaluate this polynomial a at this point x, it's straightforward if we know a even and a odd at the point x squared. So if we know this pair of polynomials at the square of these points, then it's straightforward to get a at these two endpoints. In particular, in order one time per point, we can evaluate this polynomial a of x at that point, using a even and a odd at the square of that point. So in order n total time, we can get this polynomial a of x at these two endpoints using a even and a odd at these endpoints, which are the squares of these two endpoints. This is the high-level idea of our divide and conquer algorithm for FFT. What's the running time of this algorithm? Well, let t of n denote the running time on an input of size n. We have two subproblems of exactly half the size, so 2 t of n over 2. It takes us order n time to form these two polynomials, and it takes us order n time to merge their solution together to get the solution to the original problem. So we get the following recurrence. T of n is at most 2 t of n over 2 plus order n. This is the same recurrence in the classic merge sort, and many of you must recall that it solves to order n log n. So it looks like we have an order n log n time algorithm to solve this problem. All we need is that these two endpoints satisfy the plus-minus property. So the first n are opposite of the second n. But notice we're going to recursively run this problem on this pair of polynomials a even and a odd with the square of these points. So again, we're going to need the plus-minus property for this subproblem and for all smaller subproblems. Looking for this subproblem, we have y1 through yn. We need the first n over 2 to be the opposite of the second n over 2. It'll be straightforward to define two endpoints which satisfy the plus-minus property. The challenge will be to define two endpoints which satisfy the plus-minus property, and for all recursive subproblems to also satisfy the plus-minus property. So let's dive into how we achieve that.